بسم الله الرحمن الرحيم والصلاة والسلام على أشرف المرسلين سيدنا محمد وعلى آله وصحبه أجمعين. Welcome everyone to the ninth lecture. Today, inshallah, we're going to be discussing the dynamics part. So we're done with the kinematics, what we discussed last time, which is relations between position, orientation, or pose, which is the combined orientation and position, and velocities. And let's start as usual with a recap. So when we have a setting like this, so bunch of again robot in a scenario where we have some motion capture system and some object we're interested to hold. So the first thing we start is transforming this set of abstract objects into numbers by choosing frames. So the first thing is that we attach frames everywhere to everything that's moving. And then everything we're going to be describing is by the relative pose of these frames with respect to each other. The relative pose of frame I with respect to frame K will be given by the homogeneous transformation, which is an element of SE3 and has a component which represents the relative orientation between these two frames and the relative displacement between the origin of frame I expressed in frame K. Then let's look at three scenarios so that we see the analogy between what we're doing. What you're all familiar with is point mass translation. Just if we have a point mass, which is a point in space that has no orientation, so we cannot talk about orientation when you have just a point mass. We describe it by three numbers, which is the coordinates of this point in the reference frame S that we chose. The rate of change of the configuration is given by the time derivative of that. The velocity, which is the how this object is moving, we can represent it abstractly as a vector, or we can represent it by numbers in the frame S. And then the kinematic relation is simply that the time rate, the rate of change of the position variable is equal to the velocity. This is not in general the case, because when we go to the rigid body rotation, the configuration is given by an element of SO3. The rate of change of the configuration is an element of the tangent space to the point where this vector, to the curve that's passing through this point in the manifold or on the manifold SO3. And then the angular velocity, we mentioned it's an element of the tangent space at the identity, which we call the Lie algebra. And this element of the Lie algebra, because we're using here 3x3 matrices, this also has a 3x3 matrix, but it's a special one, it's a skew-symmetric form. And then the kinematic relation between this angular velocity in matrix form and the rate of change of this configuration variable is given either by this equation or that equation. The first one, we're using the angular velocity expressed in the B frame or in the body fixed frame, which is the frame that's rotating with the body. And in the second one, we're expressing the angular velocity in the stationary frame. With this scenario or with this motivation, going from rigid body rotations to rigid body motion is a piece of cake because everything is exactly the same. Instead of working with elements of SO3, we're going to be working with elements of SE3. The velocities, which are in the element, are elements of the Lie algebra of SE3, which we call it small SE3, are called twists. And the twist in matrix form is given by a 4x4 matrix. Then one multiplied by the left or the right by the homogeneous transformation gives us the rate of change of this homogeneous transformation. And then we can represent the angular velocity or the twist by numbers. So as a vector, either in 3 dimensions or in 6 dimensions. So the angular velocity, if we're only talking about rigid body rotation, then we can represent this skew-symmetric matrix. We can go back and forth between it and between an element in R3. And if we have the twist, which is a 6-dimensional vector, okay, or just in 6 tuple, the first 3 correspond to the angular velocity and the second 3 correspond to the linear velocity. And again, we can go back and forth between elements of the SE3 or elements of the Lie algebra by simply putting these 6 numbers in this 4x4 matrix. Yes, Farouk. Okay, so the capital V without any tilde means a vector. Same for the angular velocity without any tilde is just a vector. Okay, the angular velocity with the tilde means it's Lie algebra element. The twist with the tilde also means it's Lie algebra element, which is just a matrix form. You can think of it as a vector form and a matrix form of both of these quantities.
Vector has 3.
Yeah.
Third one is V. And the since the vector is also D.
Yeah.
So
No, no. Okay. This is capital V and this is small v. I don't know if it's that. Okay. Okay. I'll try to just expand them at home. But this is a capital V and this is a small v. Okay. In my thesis and in the some of the references, especially the where I took this course with Stefano Stramagioli, he was using always T as twist. Okay, I changed that because the book of Lynch and Park, they use T for the transformation, for the homogeneous transformation, and they use the capital V. So again, it's a mess. I personally removed the T completely because the T itself, we use it also in several places to correspond, for example, to tangent spaces or to the tangent of some map and so on. So it's a notation mess, but again, so the capital V is what we're going to be sticking with. It was a hard decision to make, but again, it's just we have to choose something, and this is what we're going to be sticking with. Okay, capital V and small v. Okay. Yep.
So when talking about the dimension of a manifold, it seems like it's something that's determined by the dimension of its Lie algebra when it's mapped to Rn.
They're related, of course. They are definitely related. Okay. What do you start with the dimension of the manifold and then deduce the dimension of the tangent space or other way around? Don't go into that direction. Just for now, the dimension of the tangent spaces will be always the dimension of the manifold itself. Okay, but they have different meanings. So in this scenario, we're talking about the dimension of this point on the algebra or the like points there, but these are the dimensions of vectors. So you can think of it this way. So these are points on the manifold. These are vectors in tangent spaces. Okay? And they have the same dimension. So this is 6 dimension in this case, and this is 6 dimensional also.
See an expression for a point on the manifold. How do we deduce the dimension?
That's a long story. Okay, so what's the formal way of actually starting by some manifold and trying to get the dimension of it? It's a long story. We just skipped it for our purpose. We're going to be differentiating between 2 kinds of twists because they are the most natural ones. We said that the twist, if we go back, so this is the angular velocity in tilde form, and this is the angular velocity. Sorry, this is the twist in tilde form. And we removed here the indices because we can represent this angular velocity in any index you choose. Any frame that you have in your setting, you can represent angular velocities or twists in that frame. And of course, if we're talking about the twist, which is the relative velocity or the relative generalized velocity between frame B and frame S, then it sounds natural to represent the twist either in frame B or frame S. And then we got these 2, okay, special twists. The first one is VBSS, which is the twist of the body attached to B frame. Okay, so sorry, the body attached to frame B with respect to frame S, expressed in frame S. And this is exactly the same quantity, or in other words, the same information, but expressed with different numbers, expressed in frame B. Okay, so this is the stationary frame, and this is the moving frame. Last time we showed that simply because they are both related by that. In the end, they are mapping or different versions of the tangent vector to the of the curve that's passing on the manifold. Then we have this relation or this map between the tilde form of V and V expressed in B and S. And we derived last time that joint representation, which maps the vector form of V expressed in B and V expressed in S. The twist expressed in B and the twist expressed in S. This was the 6x6 matrix, and this was its expression down there. Okay, so you can read it down there as these are just blocks. Each block is 3x3 matrix of itself. And this is what we derived last time. Now let's look at dynamics. So this is everything you need to know about kinematics. So if you have velocities, you can always represent again, stuff moving around. You can talk about velocity of any frame with respect to any other frame. And this is all of the information that you need. Now let's add forces or torques or the combination of them when we talk about rigid body motion. So what we're going to be doing now is dynamic modeling, which is the essential part to start doing control. So that's why we're spending so much time in all of this modeling part, because later when we go to the control, the first thing we're going to starting with is the dynamic model of this system. And we need to look at what are the inputs and the outputs. Then you take the outputs, you feed them back, you design a controller, and you feed the inputs to be that. So this is the strategy. But what are the inputs and the outputs for this to these kind of systems, these elementary building blocks of robotics. When we have just a point mass, then we talk about forces. When we have a rigid body that's rotating in its place, that's not translating, we talk about torques. Then you can imagine that when we described when we used homogeneous transformations to describe rigid body motion, just translation and rotation, then we had velocities, the generalized velocities, which were the twist that described, or also angular velocity and linear velocity. Then you can expect that we're going to have here some sort of quantity that will correspond to a combination of forces and torques. This quantity we're going to be calling wrenches. Okay, so forces, torques, and wrenches. This part about forces should be trivial to you, but we're going to be formulating it in a way such that we're able to extend it to the other two cases. And you can expect that, okay, when you take something that's easy and try to make it generalizable, it becomes hard. This is what you should expect here. First, forces that are applied on this point mass. In general, they are abstract. For example, if I tell you I have a point here, and this is the force applied on it. Okay? So I'm pushing it in this direction. So for example, this point can be moving, for example, along this trajectory. And at this instance, I choose to push it like this, and then it starts to move there. Okay? You all visualize this cartoon? The point moving in this direction, so its velocity is pointing this way. It's abstract. And then at some point, I push on it with another direction, or with a force that changes its direction immediately to there. So the force is a vector. I'm not going to go into details, okay, but assume for now it's just a vector, 3 numbers, and the velocity is another 3 numbers. You can only talk about numbers once you choose the coordinates. So we have only here one coordinate frame when we were talking about point mass. So we don't attach any frames to a point that's moving, because we don't talk about orientation at this point. So we just represent this force by 3 numbers when we talk about it expressed in the S frame. This will be the notation we're going to be using for forces, and later on for torques and for wrenches. So down there in the subscript, we're going to be using, this will be called the force, the abstract force from source S, RC. Okay. This can be a gravitational force. This can be a magnetic force, can be a force from a controller, force from a propeller, again. So different forces have different sources. It's applied on the point B, and when we express it, we're going to express it in frame S. Okay, so a force and a torque and a wrench will always have 2 indices, only 2 of them. Okay, one up, and the second one up on the left. One up on the right, one up on the left. So we don't have 3 indices for forces and torques and wrenches, like what we had with velocity. Velocity was always something with respect to something expressed in a third thing. The kinetic energy, we're going to always be starting with the kinetic energy. This is something usually overlooked, but you all know what the kinetic energy of just a point mass is half mv squared. If this v is a vector, then it's half mv transpose v. And of course, we're talking about numbers here because we're transposing, you're transposing some numbers, right? You're transposing a 3 vector or a 3 tuple. Then we're talking about expressing this in the S frame. This is the only frame that we chose there. And simply, this is how the kinetic energy looks like. And it's a map that takes R3, takes a vector. You need to tell me what the 3 numbers are of V, and then I'm going to give you one number, which is a scalar. And this is very important because when we have something that's a scalar, this means what? What? No? Absolutely. It doesn't depend on any direction, doesn't depend on any coordinates. So if I choose another frame S bar or S hat or anything, and I calculate the kinetic energy, I should get exactly the same number. No matter what numbers I had for the V in both frames, when I take this quantity, I should get the same kinetic energy. So kinetic energy is a scalar quantity. Whenever we have a scalar quantity, we need to look at it from different frames and check whether we're getting the same numbers or not. So the kinetic energy of this point looks like this. How is the momentum defined? How do you define the momentum? You say, okay, it's mv, right? More generally, the momentum is defined as the gradient of the kinetic energy with respect to the velocity. This is the general definition of momentum, because momentum can be generalized even to settings that are even not mechanical in general. So we're going to be denoting the momentum of point B, and we're going to be talking about the linear momentum. So the term linear momentum, it just has a name, P V down. Okay, P sub V means it's linear momentum. When we talk about angular momentum, we're going to be using P sub omega. Okay, just this is the notation we're going to be using for linear momentum and for angular momentum. And this is when we have different bodies or different points, then we can have momentum of point 1, point 2, and point 3. We have here one point, which is B. So this is the linear momentum of point B. And then we express it in frame S. Okay? So linear momentum of point B expressed in frame S is given by the gradient of the kinetic energy with respect to the velocity expressed in frame S. And it's a function of V. In general, the gradient is a function of V. So and this is why we get it like this. You see? And then we get MV. Clear? What is the dynamic equation that governs this equation? That governs the forces applied and the momentum and the velocity. What kind of law that we use to describe this relation? Newton's law, right? Well, how do you state it? Wrong. Sum of forces, okay. The rate of change of momentum, absolutely. So Newton's law, properly speaking, is that the rate of change of the momentum equal to the summation of all forces that are applied. So if I have a bunch of forces from different sources, I need to take the resultant or the total force, which we represent here like that. But this is still not Newton's law. There's a very important condition there. Anyone remember it? No, both are equal to each other. So the rate of change of momentum is equal to the applied forces. If there are no applied forces, then we say that the rate of change of momentum is equal to 0, which means that the momentum is conserved. But there's a very important condition here. What is it? What?
Direction.
The directions, right? That the first quantity here is the first quantity here, and the second quantity here is the equal to the second quantity here, right? In general, is that true? No, that's not true in general. Newton's law is mentioned as follows. It's the rate of change of momentum is equal to the total or the resultant applied forces in a stationary frame. Newton's law is only valid if you have a stationary frame. Of course, here we're talking about have point mass and we have one frame, so it's trivial. Later on, you can imagine what will happen when we go to frames that are moving around. So Newton's law, we can only talk about it in a stationary frame. That's why we have here PVB expressed in S. The rate of change of linear momentum of the point B expressed in the S frame is equal to the summation of all forces applied on that B expressed in that frame. And of course, the mass here is just a constant, so we can also rewrite it as the rate of change of V is equal to 1 over m multiplied by the forces applied.
This law only needs to have a stationary frame, or also in the linear momentum and kinetic energy equations, I need to be expressing always in.
That's a good point. Kinetic energy can be always is defined as this norm between bracket of the velocity expressed in any frame. The momentum, I can also express it in any frame. If I multiply m by the velocity expressed in frame S bar, S hat, whatever, I'm going to get the momentum of the point B expressed in that frame. Okay? Because m is a scalar. Okay? So it doesn't matter. But again, m is a scalar, so I see it from all frames with the same quantity. It doesn't change. And so this is the summary of what you should know. So given the forces as a vector, then I have, this is simply what Newton's law says, that the rate of change of momentum is equal to these forces. And then I integrate the momentum, the rate of change of the momentum, I get the momentum, but this is the differential equation, so I need to provide the initial conditions in time. And then I multiply the momentum by m inverse, I get the velocity. I multiply the velocity by identity, I get the rate of change of the position. And then I integrate the position again, given the initial condition, I can get the position as a function of time. The first equation, which is the rate of change of the position equal to the velocity, is the kinematic relation between velocity and position. The second one is the momentum balance, that momentum is conserved, which is just what Newton's law describes. And the third one is known as a constitutive relation. It describes it. You see, the only place where the mass entered is in this equation. Because if I have a body that's this small, or a planet that I try to describe with this equation, it's the same. So only this equation changes and the rest are the same. So you see, this is why it's called the constitutive relation. Just a name in general, because this is a nice separation. Yeah, question? Again? Yep. So, okay. Clear? No typos? Okay. Of course, this is a very exaggerated way to just say what you already know, that the rate of change of position is equal to the velocity, and the rate of change of the velocity, which is the acceleration, is equal to F divided by M. Or in other words, it's just psi double dot is equal to 1 over mf, which is in the end F equal to ma. But you see, this is how it should be, because later on when you want to extend, of course, this will not be valid. This is the one that's valid. Now let's boost things up a little bit. Before we go, any questions so far? This should be trivial, right? Yep. Previous slide.
Bracket for the derivative of energy with respect to velocity.
Yes.
That bracket means
It's a function. Yes. So energy, no, it's not multiplication. Energy is a function. It's a map that goes from R3 to R. The gradient of E by an element of R3, which is the gradient of the E divided by, which is the partial derivative of E with respect to V, is another function that takes R3 to R3. Okay. So the gradient is in this way a function also.
when we look at the expression that's on the screen right now, we have B expressed in S, B with respect to S expressed in S.
You have velocity of point B expressed moving with respect to frame S, and then you look at it from frame S. You observe it from frame S. Yes.
In this case scenario, since we're talking about a point mass, we really can't have, I mean, we could have different frames of references.
Stationary, yes. And even if there is something that's moving there, it will not have any orientation, because a point mass doesn't have any orientation. That's why it will be trivial to add just a frame that's moving around. Not needed.
Exactly. So in that case scenario, though, I mean, of course, it's understandable that we always have velocities written in 3D notation, the velocity of a point with respect to something expressed in something. But wouldn't it be the same even if we take another stationary frame?
The same numbers? No. Again, you make a frame like this, okay? Then this is your Y direction. Someone else makes a frame that this is their Y direction. I'm moving in the same way. You see me moving positive number and he sees me negative number. So it's not the same number, even if they're both stationary. The numbers change. But take the norm of both, you get the same number, which is the kinetic energy in that. The linear momentum also depends on the frame. Everything take it as a rule of thumb. Anything that's a matrix or a vector depends on some basis that you chose. Otherwise, you cannot write it in this way. And this is what we started with, if you remember, when we talked about vector space, and we said, okay, we have a basis, and then you can look at this vector or this covector in this basis or in that basis and so on.
But then in this PVBS, so how do we read it exactly?
This one, linear momentum of point B expressed in frame S.
Not with respect to anything.
What?
So we don't have this.
You don't talk about momentum of something with respect to something. It has a momentum. That's it. So it's a physical quantity of the point that's moving. Okay, and it's like that. Okay, this is the momentum of the object. Rigid body rotation. Instead of starting with forces, we have torques. Again, if I have an object that's rotating, and for example, it's rotating around, I don't know, let's maybe take this object. So this is the object like this, it's rotating in space. So this is the axis it's rotating around. This is the omega bs without numbers. I still didn't represent it in any frame. and then at some point, I just apply to it a torque that makes it rotate like this. So this will be the torque that I applied at some point to make it rotate. So same idea, different axes, because I have this is a torque and this is angular velocity. The abstract torque is the torque from source SRC acting on body that's attached to frame B, and I can represent it in any frame. Now we have a choice. We can represent it in frame B, in frame S, or any other frame that we have. And that's why things will get a little bit tricky now. Kinetic energy is equal to half omega transpose J omega. Rings a bell? Half omega transpose J omega. Omega is the angular velocity, and the J here is the moment of inertia. Okay. So J is the moment of inertia. Who here is not familiar with the moment of inertia? Everyone is familiar? Okay. What's the dimension of it as a matrix? 3 by 3 matrix, right? Is it how many numbers inside that you have how many degrees of freedom do you have inside? No, completely wrong. 6. Yeah, why is it 6? Cross product, okay. Cross product, okay. And can someone beat that? Yeah.
The center of the mass.
Yeah.
3.
That's wrong. How many numbers do we have? The inertia matrix is symmetric. It's a symmetric 3 by 3 matrix in general, which means that instead of having 9 numbers, I have only 6 of them. The 3 on the diagonal and the off diagonal ones. Of course, you're saying, okay, the off diagonal should be 0. It's only if you choose a certain way of representing this body fixed frame. In general, not. So in general, the 6 numbers, if you put the frame which is attached to the body in a certain way, you can eliminate the off diagonal one, which is off topic for now. We're gonna come back to that later. But what I want to make here is that even what you just said is not right. Because when you have a matrix, you need to tell me which frame are you talking about. When I represent the inertia, the moment of inertia tensor in general as a matrix, you need to tell me which frame you're talking about. Is expressed in the frame B or in the frame S. So in general, because the kinetic energy depends, I can write the angular velocity in any frame, star. I can also represent the inertia tensor in any frame, star. Then this is the correct expression of the kinetic energy. In general, it's a function not only of the angular velocity, it also depends on the rotation matrix, depends on the angle. Okay, I'll give you a small example. You in physics back in the days, there was this example of a skater that opens their hand, okay, and then rotates slowly, and then closes their hand, and then rotates very fast. What happened there? The only thing is that the inertia tensor changed because expressed in the stationary frame, it's different because this was large, this was small. This is the idea. So it depends on, again, some configuration variable that you have. Okay, so this is just an intuition. This is not formal way of proving it. Then we're going to be talking about the formal way of showing that right now. But if this is the kinetic energy, now you can expect when we take the gradient to describe the angular momentum. The angular momentum, again, is the gradient of the kinetic energy with respect to the angular velocity. It's also a function of r and omega, and we get something like this. So angular momentum is the inertia tensor multiplied by angular velocity, yes. In any frame, that's correct. But the problem is in the inertia, the moment of inertia tensor. It can be time dependent. It can be dependent on the orientation or the configuration of the body. Euler's law says that the rate of change of momentum is equal to all of the applied torques. Again, in which frame? Only in the stationary frame. And this is where things get nasty when we talk about rigid body dynamics. Okay, rotational dynamics at least. So because Euler's law is only valid when you talk about the stationary frame. Now let's ask a question. Can we represent the angular velocity in the stationary frame? Yes. Can we represent the moment of inertia in the stationary frame? Yes, of course. But it will become a function of R. What is the frame that we represent the moment of inertia in, and it becomes a constant? In the body frame. So the angular velocity. So the angular velocity can be presented in the body frame or in the station frame, no problem, or any other frame. Newton's law is valid only when you have the stationary frame, but the moment of inertia is only constant in the body frame. And this is why when we write the Euler's equation, which is simply rate of change of momentum equal to the torques in body frame, it will become very nasty. We're going to get some terms now we're going to see. So now let's go to the board and try to derive, put formally what we mean by that. And then later we're going to be moving to the rigid body motion, and everything will be exactly the same. Instead of working with rotation matrices and angular velocities, it will be homogeneous transformations and twists, and everything will be same. Okay? So this is why I focus on this part. Any question before we move?
Constant or a function?
It's constant if you represent it in the B frame, and it's a function of R if you represent it in the S frame.
You represent
If you want to use Euler's law, you have to use the stationary frame. There's no choice about it. Right? Unless you write everything in the body frame, and then it's no longer that the rate of change of momentum is equal to the torque, which is what we're going to be proving right now. Any question? Okay, so pen and paper. Whiteboard. Let's see. So let's see. So now we're going to be talking about the rigid body rotation dynamics. The setting that we have is the following. So we have some sort of stationary frame S, and then we have some sort of body. Okay. So this is the body that's rotating, and attached to it, we have a body fixed frame, which is frame B. Now, what is the moment of inertia? This is something that would have been nice to calculate, but it would have taken one whole lecture just to go through the math. It's not that hard, and you're going to find it in chapter 4 of my thesis. So I'm going to add it in the reading material, but this is just supplementary. You can start. This can be your starting point if you don't want to spend any time. That the moment of inertia matrix is a symmetric 3x3 matrix that looks something like this. So JXX, JXY, JXZ, JXY, JYY, JYZ, JXZ, JYZ, JZZ. So it's a 3x3 matrix that's symmetric. So I need 6 pieces of information to talk about this moment of inertia. When we talk about mass, so mass, again, you understand what the concept of mass is, right? So if I apply a force, I don't move instantaneously because I need to like accelerate a little bit. What is the thing that like defies this instantaneous acceleration is just called the mass. Okay, so if I press on a point in this direction, it takes some time to accelerate depending on its mass. Same idea here. So if we have a frame and we want to rotate, in principle, I can rotate around 3 axes, right? This one or that one or that one in 3 dimensions. So the inertia around this axis alone, if the other 2 are fixed, is given by JXX. The rotation about this axis alone are by YY. The rotation about this axis alone, the ZZ, are just the 3 numbers that correspond to the mass, just intuitively. And if I'm rotating both in the X direction and in the Y direction together, I get this number. In the X direction, the Z direction, then this number gets into effect. And if I'm rotating in the Y direction and the Z direction at the same time, this number plays a role. And if I'm doing a general motion, general rotation, fixed at a point, then all of these numbers, they play into account. Yes, it's a symmetric. So XY, XY, XZ, XZ, YZ, YZ. It's symmetric. So I have 6 numbers in the end. So in the end, this is just equivalent or isomorphic to jxx, jyy, jzz, jxy, jxz, and jyz. Just 6 numbers in the end. And I just put them in this matrix form. So this is the matrix that we call the inertia. And again, because I'm talking about frames now, then I can be talking about something that's fixed or rotating. I can be talking about the B frame or the S frame. And this is where it becomes nasty, because if I'm talking, first of all, how do we calculate this? This is beyond the scope of this course. But if you represent it in the B frame, which is the one that's attached to the body, this becomes a constant. Okay. So this is what you need to know, that when I look at the moment of inertia in the B frame, in the body fixed frame, I just get 6 numbers that are written in this matrix form. How do we do it in practice? How do we do it? How did you learn about it in, I don't know, in undergraduate studies? Is that you take elementary objects, for example, like a sphere, and you calculate, you have some formulas for calculating depending on the density. You take, for example, a cuboid or a triangle or a prism and so on. These are just basic shapes. In practice, how do we do it? You go to SolidWorks or your favorite CAD program. You draw your object and you tell it, okay, I want the moment of inertia in this frame. You have to specify what is the frame you're talking about in SolidWorks before it gives you the numbers. So this is the idea. You have to tell it which frame you're talking about. And if this frame is aligned in a certain way about what are known as principal axes of inertia, you get that these 3 numbers are 0, and I get only 3 numbers, which is what you mentioned about being diagonal. Only in this frame. In general, not. So this is the moment of inertia. So now what is the the angular momentum in the B frame? So the angular momentum of the body that's attached to frame B, expressed in the B frame, is simply JB multiplied by omega BSB. So this is the angular momentum. What is the angular momentum expressed in the S frame? Because this is the one that we're interested in writing as Euler's law. So we have that P omega SB is equal to the rate of change of it is equal to the torques that are applied on B expressed in the S frame. So this is Euler's law. So the only thing we need to do is just write an expression for omega with the angular momentum in the S frame and just differentiate it by time and see what do we get. This is what we're going to be doing. When we have an angular, when we have any vector expressed in the B frame, how do we write it in another frame? What do we multiply by? Rotation matrices. So if I want to have P omega BS, and I'm given P omega B, what should I multiply by? Which R? What is down? BS. Again, you can never make it wrong. Okay. This is expressed in B, then I take from B, I express it in the S frame. And now let's do a rate of change. But before that, let's multiply this guy. Let's put it like this. And now let's take this expression. And this is JB. The omega B expressed the B with respect to S expressed in B. Can I write it as some omega expressed in S? What should I multiply it by? What is down? SB. So you see, angular momentum is equal to J multiplied by omega. Angular momentum is equal to, what is this guy? What does it act as if? Another J, exactly, another moment of inertia, but seen from a different frame. This is simply Js as a function of RBS multiplied by omega with respect to S expressed in the S frame. Okay, so these two are the same. So you see now that when we look at the moment of inertia from the body fixed frame, it's constant. But when we look at the moment of inertia in the S frame, it becomes a function of R. So now when we differentiate in time this expression, you can expect that we're going to get something like this. Rate of change of this in time multiplied by that plus this expression multiplied by the rate of change of this in time. Okay, let's do it on this one easier because this will be easier to work with. So I'm going to do the rate of change now. Let's maybe go to the next slide. Oops. So P, the rate of change of P, the angular momentum of the body B expressed in the S frame is equal to the rotation matrix that will take us from B to S multiplied by the angular momentum in the B frame. Clear? Then I'm going to substitute this term by JB omega B like that. And then I can differentiate. This term is constant when we see it from the body fixed frame. So we simply get that we have that R dot BS multiplied by this term, which, what is this term actually? What is this term? The momentum, right? So let's actually write it like that. By the way, we can even keep it, maybe let's do it this easier. Let's do it right immediately like that. So we will not expand this. Okay? We're going to be doing it later. But for now, I can write this as R dot multiplied by this plus this multiplied by P dot. So it's R dot multiplied by this angular momentum expressed in the B frame. And then I have RBS multiplied by the P dot, PB. And then I have the R dot. I can use the kinematic equation and write it as RBS omega B tilde BS P omega BB plus. And then you see I'm going to have the RBS in both sides. I'm just going to take it as a common. And I get this term. Clear? Clear for everyone? This first expression from Euler's law says that it should be equal to, so this expression should be equal to the applied torques, the total ones, applied on B expressed in which frame? In the S. Or in other words, if I'm representing the torque in the S frame, I can also rewrite it as everyone agrees? The torque that was expressed, oh, sorry, doesn't make sense. This makes sense. So the torque expressed in the B frame, when I multiply by RB with respect to S, I get the torque expressed in the S frame. So anyone sees something? Yeah, exactly. So this guy cancels with that. So in the end, the Euler's law is given by the following equation that I'm going to just rewrite it as the rate of change of momentum, of angular momentum seen in the body frame is equal to minus omega tilde multiplied by the angular momentum seen in the body frame plus all of the torques that are applied on the rigid body to make it rotate expressed in the B frame. So this is simply just conservation of momentum. And this is also conservation of momentum, but this is seen in the stationary frame, and this is seen in the body frame. Any questions? Okay. Easy? So Is the rate of change of momentum equal to the applied torques in general? No, only in a stationary frame. Does anyone know what these terms are? Maybe I can rewrite it in a way that maybe looks more familiar. Sorry, it's like it's a little bit sliding down, but let's write it like this. Maybe this makes a little bit sense. Does anyone know what this term is called usually? Gyroscopic effects, yeah. Gyroscopic torques, gyroscopic forces. It's just some term that doesn't even exist. Do you see it already? It doesn't exist. Because the rate of change of momentum is equal to the applied torques. What is this term? Is it even real? That's why it's called fictitious forces, fictitious torques. It doesn't exist. There is no force that's applied on the body that's making it look like this. It's just because I'm looking from one frame and the other. I'm describing motion from a rotating frame. So this is just the effect of me rotating, that the observer is rotating. But the Newton's law is always the same. Rate of change of momentum is equal to forces or torques or wrenches or in general. Okay? So it has always been rate of change of momentum equal to forces. It just looks nasty because I'm moving now. I'm rotating. The frame itself that I'm looking from is rotating. And this is why I get this extra term that are not real. Okay. And I'm going to prove why it's not real maybe next lecture, inshallah. Any questions so far? Easy? Now, question. It still exists because when you want to integrate these numbers, you need to do this correction term because you cannot just take the torques. This is not what Newton's law says. It's not a valid law. You can think of it in another way. If I don't have this term, I don't get conservation of momentum. And conservation of momentum is a law. Momentum has to be conserved for this thing to start to move around. So this is why it's a law. And this is simply just a correction term because we're just describing conservation of momentum from a frame that's moving. Okay. Okay, so now let's summarize this in the following picture. So if you're given now the torques applied on body B and expressed also in B, then let's go back a little bit. How do we take this and in the end talk about rotation of B with respect to S? So this is precisely what the dynamic model talks about, output and input. Okay? So this is the input to the dynamic model, and this is the output. The R, I integrate R dot. And of course, this integration we need to talk about. Hopefully, we're going to have some time to look at it in more details. What is this integration? What does it even mean? Because we're moving on a manifold, right? We're evolving on a manifold. So we need to redefine what do we mean by integration here. But again, just in the intuitive sense, I have R dot, and the R dot, if you tell me omega tilde in the B frame, I can multiply from the left by R BS, and I relate this SO3 element to R dot. And then if you give me the S map and the omega B, which is in R3, I can make it into a skew symmetric form. The omega itself is the JB inverse multiplied by the momentum of the angular momentum of body B expressed in the B frame. And this angular momentum, I can integrate P dot. Now let's move this a little bit. And now how do I calculate this momentum? What I have is simply I have two terms. I have a plus and a minus. The plus term, I add all of the torques that are applied on the body B. And there's a correction term. Okay? So there's a correction term that involves a cross product between omega and the P, both in the B frame. So I need to feed back like this guy and this guy. And of course, let's not forget that we also have here, I need to provide the initial conditions, which is the angular momentum at time 0. And I also need to provide the rotation matrix at time 0, which is simply what is the initial orientation I started with and what was the initial velocity or initial momentum I had when you started this simulation or this time integration. And we also have something here that I also, after integration, I feed back this guy here. So this picture is simply the dynamic model of a rigid body that's rotating. Torques, from torques, and then I have as an output angular velocity and position, okay, or orientation. So let's summarize them. So R dot BS is equal to R BS omega tilde. P dot is equal to minus cross product with P plus torques. And then we have the constitutive relation, which simply says that the angular velocity is nothing else than the J of B expressed in the B frame multiplied, inverse, multiplied by the linear angular momentum in the B frame. So kinematic equation, momentum balance, constitutive relation. Easy? Okay. Try to do it with Euler angles. You're gonna regret your life. Okay. It's not as beautiful as this. Because simply, now we can talk about the spaces, right? This is an element of SO3. This is a tangent space, element of the tangent space. So it's a vector in the tangent space. Yeah, element in the tangent space. This is an element of the algebra. This is an R3 vector that's just isomorphic to that element. This is a covector, properly speaking, without saying what that is now. And this is the rate of change of that covector, or an element of the dual algebra. And then torques, and simply this is just the dynamic part. Rigid body rotations, the kinematics are nonlinear, and also the momentum balance is nonlinear. That's why just doing rigid body rotations is hard. You cannot do linearization and try to do simple stuff. You can do, of course, linearization and try to do simple stuff, but in general, it's nonlinear, just from the start. Even if you don't need to do any flips or anything, it's nonlinear by itself. And that's it. Any questions? Yeah. Yeah. Yes.
So how can I feed it back? It's in the middle of the scheme.
Yeah.
So it's needed to calculate what is after it.
Yeah, that's why it's called a differential equation, right? It's x dot equal to ax, right? So x dot is equal to ax, for example. So if I integrate x dot, I get x, and how to calculate ax dot, I need to multiply it by a. So I have this.
A is known.
A is known, yeah.
A is known, but here is RB.
Good question. So A is a function of x multiplied by x. Then it's nonlinear. So that's the difference. So nonlinear equations, again, they have something like this. So I cannot calculate this without knowing that. It's not just, this is nonlinear in terms of this. So the dynamics of R and P together are nonlinear. Okay. It's not a matrix multiplied by. That's why what I started with this course, linear algebra fails. You can no longer talk about linear algebra. You see, and this is the very important point. We're talking about matrix multiplication, right? So this is, everything is matrix multiplication, but you can imagine how much is the math behind, right? So for example, this rotation matrix, I multiply by some angular velocity and I get R dot. and this is a rotation matrix. But you see, each one of these brackets is a completely different space, and they're all mapped together on SO3. Okay. Now let's go to SE3 in 10 minutes. Okay. Inshallah, it will only take 10 minutes, just by analogy. I'll just sketch first the proof, again, just the math, and then we're going to write it down very quickly. Imagine that everything now we're talking about is something that's rotating and translating at the same time. So this frame is no longer fixed at this point. It's also moving. Okay. So the inertia tensor, first of all, what is the equivalent to the angular velocity when we talk about rigid body motion? Is a twist. What's the dimension of it? 6/1. What would be the corresponding inertia that's multiplied by it? A 6/6 matrix. What would be the momentum? A 6/1. The first three would correspond to angular momentum. The second three would correspond to linear momentum. Same like with the twist. The first three corresponded to angular velocity. The second three corresponded to linear velocity. The inertia tensor, which will be a 6/6 matrix. When we look at it from the body frame, it will be fixed. When we look at it from another frame, will not be fixed. Newton's law in general says that the rate of change of the angle of the total momentum, the generalized momentum variable, expressed in the stationary frame, will be equal to all of the applied wrenches. We're going to be using W to correspond to the combination of linear forces and angular forces, which is torques and forces. When we use this term, how do we represent the velocity or the twist from one frame to the other, going from this frame to that frame? What is the transformation that we use to relate the twist? No, the adjoint matrix. So the adjoint is a 6/6 matrix that will relate us from the twist in frame S to the twist in frame B. Then what you see inside of here will be not R, J, R, will be adjoint the generalized inertia matrix, which will be 6/6 multiplied by the adjoint, one which is the inverse and one is the transpose and one is not the transpose. We're going to see. And then later, when we differentiate this guy, we're going to need to take the rate of change of the adjoint, which will have some sort of, okay, we're going to need to look at some math. And in the end, we're going to get something very similar to this. The rate of change of the generalized momentum will be equal to some fictitious forces plus the applied wrenches in the body frame. Okay. So this is the sketch. Now let's do it very quickly. So rigid body motion. The generalized inertia tensor we're talking about, again, of body B expressed in B, is a 6/6 matrix that's also symmetric, and it looks like this. It is J in the top three, in the top left corner. It is the mass multiplied by an identity matrix in the top and the bottom right corner. And in the rest, we're going to have some terms here. I'm not going to write them now for now. There is a way to make these elements disappear. And this is simply by choosing the body fixed frame to be attached to a very special point on the body. What's that point? The center of mass. So there is a very special point on the body, on any body. How do we find it out? Again, open SolidWorks, take your body, draw it, put all of the dynamics information about the density that you know, the materials that were used to design it, and to tell you, okay, the center of mass is in this precise location. It's a very special point. So if you put this frame B on the center of mass, these disappear. Okay? But in general, not. Okay? So just keep that in mind. Let's assume for simplicity that we're going to be using we're going to be putting the B at the center of mass frame. Very good point. First, the inertia tensor, okay, the generalized inertia tensor is a symmetric 6/6 matrix. This is the most general thing that you have. To choose a frame B, put it on the object that you're talking about, the rigid body, the end effector of the robot, the frame that's moving with the robot body itself. This would be a 6/6 matrix. Put this frame on the center of mass, these two disappear. align this frame with the principal axis of inertia, this becomes a diagonal. So in the end, this becomes a diagonal 6x6 matrix only if you choose the center of mass and align it in a certain way. Okay? But in general, it's a symmetric matrix like this. Let's keep it general. The twist in frame S is equal to the adjoint, VS. Okay. VBS. What are the indices? What is down and what's up? B down, S up. 6x6 matrix that will multiply these two together. How do I define the generalized inertia? Sorry, the generalized momentum. The generalized momentum, we're just going to be calling it P without any subscripts. And it will be of body B expressed in the B frame. And this is equal to the inertia tensor BB multiplied by the twist in BS. And of course, we can expand it a little bit. We can write it down like this. So this is JB M. And then we have the off-diagonal terms. And this is multiplied. What was the twist? Had in the top the angular velocity term. And below we had the linear velocity term. So you can see that the top part of this one also we're going to be calling the angular momentum. And the lower part will be the linear momentum. But you see, when we're talking about something that's rotating and translating at the same time, the momentum changes a little bit. It's no longer just J multiplied by omega and M multiplied by V. Only if you have that this is placed at the center of mass, that this is truly the case. Okay. So this is why this is more general. Clear? Okay. So the rate of change of momentum expressed in the S frame is simply the rate of change of the adjoint transformation of PBB from B to S. What we need to do now is what is the rate of change of the adjoint matrix? So we're going to have here the rate of change of the adjoint multiplied by the momentum, the generalized momentum, plus the add multiplied by P dot. Everything was exactly the same. We're just following same drill. And what we get is the following, that this is equal to the adjoint multiply the very special map that again has something to do with the Lie algebra and with the Lie group, but there's no time to go into details of it. But we call it the small AD, and it's a map that takes the twist as a function. Multiplied by P. I think this should be transpose. I'll check this out. Okay, but I think this is correct. I think it will be a transpose here. Plus, we have P dot BB. This one, BS. No, this is correct because this is the generalized momentum in the B frame. Absolutely. Yeah, absolutely. Very good point. Yes, absolutely. This should be transpose. Yeah. And this should be SB. Yeah, thank you. SB transpose. Let's move this part a little bit. SB. Yes. And now we're not going to move on. okay? Because we need to just very big pause. Why is this a transformation from B to S in this weird way? Again, so why didn't we just take this P from B and then we multiply it by BS and then we just get the momentum there? This is because something that we skipped, we mentioned very quickly, and we didn't talk about it in details. And I'm just gonna throw the bomb now, and we're gonna continue it from on Tuesday, inshallah. And we just have 3 minutes left. So the bomb is the following. Twists, which are elements of SE3, or again, so the twist tilde in any frame, right? That's without even frames. The twist in general, when we map it to an element from R6, it's angular velocity and linear velocity. This came from an element of H dot, right? And the H dot was the tangent space with respect to H of SE3. You all agree? What about the momentum? The momentum came from the definition that we took the gradient of the kinetic energy and we divided by the twist. The gradient is not a vector. That's the bomb. The gradient is not a vector. The gradient is a covector. And that's why momentum is also a covector. And that's why range, which is when we talk about the rate of change of momentum, is equal to the applied forces, which are the generalized forces, torques and forces together, is also a covector. Covectors, why do we say covector and vector? Remember what, does anyone remember what the definition was of a covector was? It was a linear map from this vector. So when we have a vector space V, we said that V star is the dual space, and elements of V star are covectors, and elements of V are vectors. Why is it that we're saying that this is a covector and this is a covector while the twist is a vector? The answer is very easy. Look at how they change coordinates. So you can always know the true nature of the variable that you're having simply by changing coordinates and seeing what does the transformation look like. Anything that transforms in the same way should belong to the same space. Any two things that don't transform the same way don't belong to the same space. So the bottom line is, and this is something we're going to be doing next time, inshallah, that when we have the twist in the S frame, and I want to transform into it the twist in the B frame, we use the adjoint from B with respect to S. If I have some wrench in the S frame, and I want to represent it in the wrench on the wrench in the B frame, I need to use H, B, S transpose. For now, take it as a law. Next time, we're going to be proving and starting from here, inshallah. Okay. So thank you very much.